examples concerning arranging items that are always together. In this presentation, you will learn how to arrange items that are always together by treating the joined items as if they were one object. But before, let us recall the fundamental counting principle, which states that if there are m ways to do one thing and n ways to do the other thing, then there are m times n ways to do both things. This fundamental counting principle is important. At each point where I'm going to use it, I'm going to mention. Example number 1. A, in how many ways can 3 women and 2 men sit in a row? B, in how many ways can 3 women and 2 men sit in a row if a man and his wife must sit next to each other? So before we give solution to A, we need to understand that here we have 3 women, 2 men, supposed to sit in a row. What does this mean? It means that 5 people occupy 5 seats. Therefore, here is a table. I have seat number 1 up to seat number 5. Possible occupiers. I'm saying on seat number 1, any of the 5 people can sit there. And once it's filled, I'm left with 4. Seat number 2, any of the 4 can sit there. Once it's filled, I'm left with 3. Any of the 3 can sit there on seat number 3. Once it's filled, I'm left with 2. Any of the 2 can fill seat number 4. Once it's filled, I only have 1 person for seat number 5. But what is important to note is the 5 representing 5 people. That means we have 5 choices on seat number 1, 4 choices, seat number 2, and so on and so forth. Meaning, filling the seats, we have different choices. But then the question would be, how are we going to sit them together? This is wherein the fundamental counting principle comes in, which allows us to say, all together, they can sit in a row in 5 times 4 times 3 times 2 times 1. That is fundamental counting principle, right? But this, as it is written, it simply means 5 factorial, which is simplified to 120 ways. So this is the solution to number A, and you have seen where the fundamental counting principle comes in. Let us now look at number B. Right, we still have 3 women and 2 men, but there is this condition: a man and his wife must sit next to each other. Now, understanding that, we are simply saying the man, let it be M, can sit to the left or right of his wife. Say W, which could also stand for women, in such a way that the man can be on the left, then the woman right, or the woman left, then the man right. Or it could have been vice versa on this situation and this one, so that here the woman is on the left, the man right, the man left, the woman right, isn't it? But then this analysis is not important because it's not part of the problem. The problem we have is we want to make sure as we make our arrangements, the man and his wife are next to each other, right? So if we are now to analyze in how many ways they can sit, the 2 of them, in the 2 seats, we are saying here is seat number 1, right? Possible occupiers. Any of the 2 can sit here. Then once it's filled, we are left with 1, then can sit seat number 2. But together, in how many ways can they sit together? Again, we apply the fundamental counting principle, which simply states that the couple can sit together in these two times one, right? Which gives us, this is 2 factorial ways. So the couple can sit in 2 factorial ways. Now, how many sitting arrangements are there for the couple? Right, we need to understand when we refer to sitting arrangements and the number of ways, those are 2 different things, as we shall note as we go. So here is a situation. These are the 5 seats. And I'm saying the couple will occupy seat number 1 and seat number 2. That is a possible arrangement. Once this happens, all what it means is we are saying the man, the woman, then the other 3, right? That is when you write this in letters, but in this table, they are going to occupy seat 1 and 2, right? What is yet another arrangement would be moving the person on seat 1 to 2, 2 to what? To 3, right? So they can again sit in this arrangement, right? And this can be represented in letters like this. But the other 3, obviously, they will sit the other 3 seats. Or another arrangement would be seat number 3 and 4, right? And in words, it can be represented like this, right? So as such, again, the last one would be seat number 4 and 5. These are just arrangements, not ways to say if they sit in the first arrangement, we are fine, they are next to each other. Or if they sit in the second arrangement, still we are fine, they are next to each other, and so on and so forth. So these are what I'm referring to as sitting arrangements. So as you can see now, the question is how many sitting arrangements are there for the couple? So the sitting arrangement that are there is when you count the first table, 1, 2, 3, 4, meaning the first arrangement could be seat number 1 and 2. The second could be seat 2 and 3, then 3 and 4, then 4 and 5. So as you can see, we are simply pushing 1 seat in front, so that maybe in a way we could have avoided drawing all these 3 tables and only drew this, but then as we try to check on the sitting arrangement, it will be like the first arrangement is 1, then 2, 3, 4. You are still going to come up with the same number, knowing as you do that when I say 1 for seat 1 and 2, then when I say 2, that means we are moving 1 in front, 3, 4. So you still come up with this, but I have done this so that at least you understand what is referred to as sitting arrangement. So arrangement number 1, arrangement number 2, arrangement number 3, arrangement number 4 on the part of the couples. Okay. So answering our question, of course, I've already said it, but there are 4 sitting arrangements, and in each sitting, the other 3 people can sit in 3 times 2 times 1, which is equals to 3 factorial. In each sitting, that means this is sitting number 1, right? They can sit in this. This is another sitting number 2, 3, 4. So those are the 4 sitting arrangements. But for the 3 people, if we consider sitting number 1 as if that's the one that they've used, or what it means for the 3 people, they have to occupy these 3 slots. That means 3, seat number 3, n of the 3 can occupy. Once it's occupied, 2 are left, n of the 2 can occupy seat 4. Once it's occupied, we are left with 1 for seat number 5. This is where in applying again the fundamental counting principle, we multiply the 3, the 2, and the 1 to give us the number of ways the other 3 can sit in any sitting arrangement. So we have 4 possible arrangements for the couple and the other 3 people. That means if we take this arrangement, which is the first table, that's an arrangement. The couple is there, the other 3 are there. Or if you could take this or this or this. So there are 4 possible arrangements. That is all what it means. So this is important because it is going to help us understand as we go forward. Now, if I am to treat the couple as a single entity, it's as if we now have 4 seats. That is now, these are the 2 seats that the couple is what is occupying, right? So now I've queued it into only 1 seat, right? So at the end, if it is 1 seat, then 2, 3, 4. We are now having 4 seats, right? Because I've queued the couple into 1 seat. Once I've done that, how can this help us avoid finding the seating arrangements for the couple? Remember, from the tables that we have seen previously, we had to come up with the 4 tables in search for the seating arrangements for the couple, right? But I'm saying, once I've treated the couple as if is a single entity, how is this going to help us avoid that coming up with 4 tables, trying to find all the possibilities? First, let us understand that we have seen that there are 2 factorial ways for the couple to sit together, and this can occur in 4 sitting arrangements. That means the number of ways now we can position the couple is 4 for the 4 sitting arrangements times the 2 ways each arrangement is going to happen, right? So this gives us the total number of ways we can sit the couple. Also, the other 3 people can sit in 3 times 2 times 1, which is 3 factorial. We have seen that, right? Then together they can sit in 4 times 2 factorial for the couple times 3 factorial for the 3 people. But this can be rearranged. That is 4, this one times the 3 factorial times the 2 factorial. But then if you look at this, this simply represents 4 factorial. So I'm going to substitute by 4 factorial, which is the one now in blue, times the 2 factorial as it is. Once simplified, it gives us 48 ways. So I'm saying with the approach of coming up with 4 tables in trying to search for the seating arrangements for the couple, right? We can come up with the solution in this matter. Again, I need to make mention of the fact that when I multiplied 4 times 2 factorial, this one, times 3 factorial, I was using the fundamental counting principle because arranging the couple, I arrange it in 4 times 2 factorial ways. Arranging the 3 people, I do it in 3 factorial ways. Together, we multiply them. That is the fundamental counting principle, right? But then let us analyze the 4 factorial, what it could mean, right? We are saying ways that the couple sits with the other 3. That means if you consider a couple as 1, then the other 3, we are getting 4 factorial times the ways that the couple sit together, right? This can be understood clearly now that I was asking the question, how can this help us avoid finding the seating arrangement for the couple? Because I had queued the 2 seats to 1. At the end, I'm having 4 seats, which is what I'd written there. So in essence, I'll be like, now I have 4 seats for 4 people. So Since that is the case, that means the first seat, n of the 4 can sit. Once it's filled, we are left with the 3. Then second, n of the 3. Once it's filled, we are left with the 2. The third seat, n of the 2 can sit there. Once it's filled, you are left with the 1 to occupy the first seat. But these are different choices for the 4 seats that we have. Together, it will be 4 times 3 times 2 times 1. That is fundamental counting principle, which simply means 4 factorial, which is what we have here. So this is where I wanted to arrive at, starting with the tables so that you see exactly what is happening and why it is happening, right? Then we had to come up with the 4 seating arrangements. But I'm simply saying the killing of the 2 seats to 1 is the one that I'm trying to show you here, starting from what we had. So in essence or in conclusion, we are simply saying treating the couple as a single entity gives us a straightforward method of solving the problem of having the couple always next to each other in the seating arrangement. So this is what is important to say. Instead of drawing those 4 tables, you could simply have killed the 2 seats that considered as 1, then add to the other 3 to come up with the 4 seats. This is the situation. Then when you were to then find this arrangement, then you multiply with the ways that the couple can sit together. And I emphasize again to say ways and arrangements are different things because the couple have to occupy 2 seats, but in how many ways can they occupy those 2 seats? In 2 factorial ways. So once you kill the 2 seats, you come up with 4, then you find in how many ways you can sit those 4 people now. When you get that, then times the number of ways the couple can sit together. This is where we are now. So going forward, I'm simply going to apply this straightforward method of killing some seats, then consider the reduced seats as if they are now less than the original seats. Right, example number 2. 5 boys and 4 girls go to the movies. They are all seated next to each other in the same row. If all the friends are seated randomly, calculate the probability that all the girls are seated next to each other. Right here, of course, we want to find the probability that they are seated next to each other. But to find the probability, we should find the favorable outcomes over the possible outcomes. Our favorable outcomes is the girls seated next to each other, right? So all what it means now is we need to arrange these 5 boys and 4 girls, that is 9 people, where we make sure that the girls are seated next to each other. Once we achieve that, that number we get constitute the numerator for the probability. Then the denominator for our probability fraction would simply then a question of in how many ways can we sit 9 people, right? Then once we have that number, then our probability is there. So to start with, we are saying here are the 9 seats, but I want the girls to always be next to each other. And how many girls do I have? 4. So the girls are going to occupy 4 seats, 1 up to 4. But we need to know in how many ways the girls can sit on those 4 seats. The first seat, any of the 4 girls can occupy first seat. The second seat, once the first seat is filled, any of the remaining 3 can occupy the second seat. Then once it's filled, we are left with the 2 girls. Any of the 2 can occupy seat number 3. Once it's filled, we are left with the one who will fill seat number 4. So this is what is happening. That means the way we are filling the seats 1 up to 4, we are doing that in different choices. But together, what is it? It's simply 4 factorial. That means 4 times 3 times 2 times 1, right? That is the fundamental counting principle, giving us 4 factorial for the girls. This is the number of ways they can sit those 4 seats. Now, in terms of the arrangements, I'm not going to go that route, but I will explain at some point. But straight away, I want to use the method where I'm supposed to keep the 4 seats into 1, right? So treating the 4 girls as a single entity, that means now we have 6 seats to sit on. This is the situation. I've killed all these 4 seats. It's now 1 seat, 2, 3, 4, 5, 6. So we now have 6 seats, right? So I can now write my 6 seats, simply avoiding to write 1, 2, 3, 4, which I've killed them into 1. So I now have 6 seats. So this is now the new table. So 6 seats to fit in 6 people. The first seat, n of the 6. Once it's filled, 5 are left. Seat number 2, n of the 5 can occupy, n of the 4, and so on and so forth up to seat number 6. So in how many ways can we sit them? Applying the fundamental counting principle. 6 times 5 times 4 times 3 times 2 times 1, which is the same as 6 factorial. So 6 people can be seated in 6 seats in 6 factorial ways, right? I've already calculated how many ways the girls can sit in the 4 seats. Therefore, different ways when girls are seated next to each other is 6 factorial times 4 factorial. That means the number of ways the girls can sit with the other people times the number of ways they can sit on their 4 seats, giving us 17,280 ways of sitting the whole group where the 4 girls are always next to each other. Now I'm trying to go back a bit to my example in number 1, where I drew the different tables, 4 of them, in trying to check the seating arrangements, right? And I told you that, like in our case now here, the fact that the 4 seats is 1. So when I go to seat number 5, I will be saying 2, 3, 4, 5, 6. So the number of arrangement that I can have, there are 6, right? But for each arrangement, it will be 4 factorial for the girls, isn't it? So in how many ways the girls will sit, it will be 6 times 4. That is 6 times 4 factorial, isn't it? But remember, when we killed the 4 seats, how many seats are left? 1, 2, 3, 4, 5. So in how many ways the 4 people, 5 people now can fill these 5 seats in 5 factorial ways. So I'm saying the number of ways the girls can sit, 6 arrangements times 4 factorial, giving the number of ways the girls can sit, times the 5 factorial for the other 5 people. Again, I can rearrange this. It will be 6 times 5. This 5 and 6, right? Times the 4 factorial. But this 6 times 5 factorial is the same as 6 factorial, which is this one times the 4 factorial. And you see that this number is still the same as this. So the new method works of treating the 4 girls as a single entity. Then you look at what is left, right? So now we have now found the favorable outcomes, arrangements where the girls are always together, the 4 of them. So probability that all the girls are seated next to each other is 17,280 over, there are 9 people. The way we can settle 9 people is 9 factorial, because 9 sits 9 factorial, which is what I have as my possible outcome. So when this simplified, you get this is 1 over 21. So this is it, but otherwise the main focus is on trying to treat the couple or the girls as they are given as a single entity. Once that's done, then when you then sit the resultant number of people left, then the number of ways multiplied by the number of ways the girls can sit on the 4 seats. Okay. Let's look at example 3. A group of 3 South Africans, 2 Australians, and 2 Englishmen are staying at the same hotel while on holiday. Each person has his or her own room, and the rooms are next to each other in a straight corridor. If the rooms are allocated at random, determine the probability that 2 Australians will have adjacent rooms and the 2 Englishmen will also have adjacent rooms. Right. Of course, again, it's probability, but you look at what is the favorable outcome. How can we make sure that here we have 3 South Africans, 2 Australians, and 2 Englishmen? How many are they? They are 7. So if we are talking of rooms, then we are supposed to put them in 7 rooms, 1 for each. But the fact that we want to find the probability that the 2 Australians are next to each other, the 2 Englishmen are next to each other, then what does that mean? That means we are going to put the group of 7 into rooms, but we make sure that the 2 Australians are next to each other and the 2 Englishmen are next to each other. So this is the situation. My rooms 1 up to 7. 2A, I've put an A to differentiate to refer to the Australians. Then an A is simply 1 Australian, isn't it? So we are saying in room number 1, they are next to each other. The 2 Australians, any of them can be put in room number 1. Once it's filled, one of them will go into room number 2. The same can be said the room 6 and 7. Any of the 2 Englishmen can occupy room 6. Once it's filled, the other one will occupy room 7. But there is nothing particular about putting them in room 6 and room 7, room 1 and room 2. But I've done that so that when I kill, it will be clear on what is it that I'm doing, right? So at the end, we need to know in how many ways the Australians can fit in the 2 rooms. So it will be 2 times 1, which is 2 factorial. For the Englishman, the same, 2 times 1, right? So it will be 2 factorial, 2 factorial, right? Now I'm going to kill these 2 rooms and kill these 2 rooms and see what happens. So treating the pairs as single entities, that means now we have 5 rooms to occupy. So if this is now 1, then 2, 3, 4, 5. So we are now left with the 5 rooms to occupy. Therefore, this is all what it means. I've queued room 1 and 2, then room 6 and 7. So as a result, I'm now left with the 5 rooms to occupy 5 people, right? So as such, we are saying the first room, any of the 5 people can be in that room. Room 2, once this is filled, any of the 4. Room 3, once this is filled, any of the 3. Room 4, any of the 2. The last one, the last person. So these are different choices for each room. Together, in how many ways can it happen? Applying the fundamental counting principle, it's 5 times 4 times 3 times 2 times 1, which is simply 5 factorial, right? So the fact that I know in how many ways the Australian can sit in their rooms, or in how many ways the Englishmen can also sit in their rooms. Therefore, I'm now simply saying Australians adjacent and Englishmen adjacent. That means 5 factorial these terms, the Australians 2 factorial terms, the Englishmen 2 factorial, and this reduces to 480 ways. So we are now having our favorable outcome. We now want to go on to analyze the possible outcome. How can the 7 people be placed or be seated in their rooms, right? So it simply means 7 factorial. So as such, the probability then is 480 over 7 factorial, which is equal to 2 over 21. So in this example that you have seen here, the idea I'm still trying to emphasize to you the issue of treating a pair, a couple, you name it, as single entity, as long as you want them to be next to each other. There is a need for you to kill that situation and consider it as one. So this is all what I thought I could share with you.